So in the last class we discussed the plane stress problem and the plane strain problem of elasticity, of planar elasticity, and there we saw how we can do the finite element formulation from the weak formulation that we derived. We also discussed how to handle inclined boundaries, boundary conditions imposed on inclined boundaries, because in an actual structure we are going to have tractions and displacements specified normal and tangential to the edge. Here we are going to continue our discussion further with the planar elasticity problem, and as we had done in the one-dimensional problem of the bar and the beam, we will continue here with the desire to obtain a better state of stress from the finite element data that has been obtained. That is, we are interested in the post-processing of the stress information. Okay. So here, what do we mean by post-processing of stress information? So for that, let us take a simple example. That is, I have a domain. Let me draw a big domain. Okay. Let's say in this domain I make a mesh. So I make a mesh. I'll be making a mesh of triangles. Okay. And okay, here is my mesh of triangles. Let's say that I'm interested in obtaining the stress information in this element tau. Okay, in this element tau. So what do? I take a one element neighborhood of the element. That is, I will take all these elements okay. This one element neighborhood of the element of interest forms a patch. This will be patch corresponding to the element of interest tau. Okay. So you have to understand that here what we have done, you see that I have taken all the elements which share either a node or an edge with the given element. Okay. All this, the set of all these elements including this element, forms the patch which I have marked with this line. It forms the patch p tau. Okay. So this is the one element neighborhood of the element tau. Given this patch p tau, now let us see how we can construct a better stress information in the element tau. So remember, our goal was the element tau. Okay. So let's say, just to fix ideas, we take the order of approximation p is equal to 1, that is linear approximation. Okay. In this case, my state of stress would come out to be, because the strains will be piecewise constant, that is constant in the elements. So the state of stress would be piecewise constant. So now what do? We say that we will have the stress vector, we are writing in the engineering connotation, coming out of the finite element solution, sigma Fe. This is constant in element tau. Okay, and it is piecewise constant in each of the elements. So in the patch p tau. So then we say that out of this we want to get a so-called better or post-processed state of stress in the element tau, okay, given by sigma star, smoothened or post-process stress in tau. Okay. How do I represent the sigma star? So sigma star will have sigma star xx, sigma star yy, and tau star xy. These are its components. And what do? We are going to represent them using the same order polynomials as the order of approximation. So in this case the order of approximation p was 1. Okay. So for fitting the sigma star we are going to use a linear functional representation over the element tau, actually over the whole patch p tau. Okay. So what we are going to do is, so here it will be equal to a1 tau plus a2 tau x plus a3 tau y. Similarly, sigma yy star will be b1 tau plus b2 tau x plus b3 tau y, and this is c1 tau plus c2 tau x plus c3 tau y. So remember what we have done, we have taken the post process or the smoothened stress, okay, in the patch p tau to be a polynomial of the same order as the order of approximation, while the finite element stress would be of an order 1 less than the order of approximation, because if the order of approximation is p, the derivative of the functions u, v, w will be of order p minus 1. So the strains will be of order p minus 1 and the stress will be of order p minus 1. So this is one order less than the order of approximation, this is of the same order. Okay. We could do different things also, but this is what we are going to stick with. This is a simple procedure and that's what we are going to use. Okay. Now, what do we need to find as far as this is concerned? If we can get these coefficients a1 tau, a2 tau, a3 tau, b1 tau to b3 tau and c1 tau to c3 tau, then I have the representation of sigma xx star, sigma yy star, tau xy star in the element tau. But remember that to get these coefficients we are using the information from the patch p tau. Okay. So what do? Then we define a functional associated with the element tau. Okay. This is equal to sum over all the elements L belonging to the patch p tau, which includes the element tau, of integral over the area of the element L, okay, into the vector sigma star minus sigma Fe transpose into C inverse into the vector sigma star minus sigma Fe dA. See what we have done. This quantity is actually, this is the complementary energy corresponding to the stress given by sigma star minus sigma Sc. So this is the complementary energy of what we would say as the error between the smoothing stress and the actual finite element stress. Okay. So we have defined this function. What we want our coefficients. So we want coefficients A1 tau, A2 tau, A3 tau up to C3 tau such that J tau is minimized. So you see that we have defined a functional. This functional will always be positive, whatever be your stress, state of stress, right? So what we want these coefficients A1 tau to A3 tau, B1 tau to B3 tau and C1 tau to C3 tau in such a way that it leads to the minimum value of J tau. What does it mean? That this implies we have del J tau del AI tau is equal to del J tau del Bi tau, this is equal to del J tau del Ci tau is equal to 0. This is the condition that we have for I is equal to 1 to 3. So you see this gives me 9 equations it gives me for the 9 unknown coefficients A1 tau to A3 tau. And remember that in this patch, this quantity, this and this are known data. Okay, this sigma star is the one that we are trying to solve for. Okay, so just like we did in the one-dimensional case and for the bar problem and the beam problem, we can do the same thing here to set up the system of equations in terms of the coefficients Ai tau, Bi tau and Ci tau, solve, get the representation of the state of stress, recovered state of stress in the element tau. Okay. This way I keep on moving. So I go from one element to the next element. So if I am interested in this element tau, I take the one layer neighborhood of that element tau. If I am interested in the next element, I take the one layer neighborhood of that element. So this can be nicely written in an algorithmic way. And you see what again is the advantage, let me reiterate it, that here we are solving small problems over each element. For example, here the size of the problem is 9 by 9. Okay, solving these small problems does not take any time. In fact, it takes negligible time with respect to the solution of the actual finite element problem. Okay, so this job gets done very quickly as compared to the cost of obtaining the finite element solution. Okay, and that should be one of the criteria for using for deciding whether a post-processing technique is going to be useful to us or not. Okay, if I spend a lot of effort in post-processing, okay, it's better to resolve the solution with a higher order approximation. Okay, So how do we generalize? So generalization is if approximation, let approximation be of order p. Okay. If the approximation is of order p in all the elements of the domain, then this implies the finite element stress is of order p minus 1, as we said, because the strain is of order p minus 1, so the stress becomes of order p minus 1. So then what do? We want sigma star, the recovered stress in the element tau, to be of order p. Okay. So in this case, each component of the recovered stress vector, as the way we have written, will be a polynomial of order p. So how many terms will each one will have? So it will have essentially, so each component will have p plus 1 into, from the Pascal triangle, in p plus 2 divided by 2 terms. Okay, this into 3 will be total number of unknowns for which you have to solve in order to get the representation for the recovered state of stress. So what will this be? For example, sigma star xx will be a1 tau plus a2 tau x plus a3 tau y plus a4 tau x squared. So we continue, plus am tau y to the power of p, and the same representation in terms of bi's and ci's for sigma yy and sigma and tau xy. And what is m? M is p plus 1 into p plus 2 divided by 2. Okay. So we follow the same procedure that I had given earlier in order to get the recovered state of stress. Okay. What you can see then is this recovered state of stress will look a lot better and smoother as compared to the actual finite element data that you have obtained. Okay. Let me go back here and pose another problem. Let's say that in this domain I had taken a different material in this part, different material in each of these parts. That is, I will have here material M1 in this region, material M2, M3, M4. Here we have taken the boundaries of the material domains to be nice straight lines. In general, they need not be like that. When you have a multi-material domain, you will have a domain like this with different materials in the various regions. In that case, what should you do? You should make the mesh in such a way that the boundaries of the domain, the material domains, are honored. That is, the elements do not cut across the material boundaries. Okay, and at the point of intersection, like these points, okay, of the material domain with the domain boundary, or between two material domains, for example here, okay, at these points you have to have a node. So when you make the mesh, ensure that these points are nodes. Okay, then only you can go ahead and make the rest of the mesh. Okay, for example, I am making in this piece here. Okay, this should be very clear, otherwise your solution, the finite element solution, will be very far from the actual solution to the problem. Okay, so this way we could complete the mesh here in this part, and we continue the same thing in the other region. This is one more thing that you have to keep in mind when you are doing the finite element approximation, because Nobody tells you that the material will always be of the same type. You could have different types of materials. Let's go to another issue which now we can handle. Okay, let's say that I have a domain like this. Okay, this is the domain. Let's say I have, for simplicity, fixed this edge. Okay, and I have some distributed forces and some tractions acting in different parts of the domain. Okay, what do we know? That this edge is actually a crack. This is an edge crack. Edge crack. Okay, at the crack tip you will see that the solution is singular. Okay, what about this point? If you see, so this, let me call this point A. You see this point B. Here this is a so-called re-entrant corner. Okay, even here the solution is singular. What does it mean, solution is singular? It means the state of stress goes to, the stress components go to infinity at these points. Okay, some of the stress components go to infinity. So in general, if I take this crack, the crack will have a representation as the vector u, the exact one, will be equal to some vector v into r to the power of alpha. Okay, now this v is a function of alpha and theta into r to the power of alpha. What is r? R is the distance from this point to any point in the vicinity of the crack. So this is the distance. Okay, and I can take the angle to go theta like this. So I use a local polar coordinate system in the vicinity of the crack or again of the re-entrant corner. Then the solution has this form. Okay, and because of which the strain will have r to the power of alpha minus 1, and generally this alpha will be less than 1. So what happens? This quantity now becomes r to the negative power. Okay, if it's r to the negative power, then as I come closer and closer to this point or to this point, okay, this strain will go to infinity. That's what we mean by singularity of the solution. This alpha in the vicinity of the crack is half. Okay, if it's an isotropic material. In the vicinity of this corner, it will be alpha is, it could be 1/3, 2/3, different quantities. Okay, so you see that this tells me, depending on the various profiles of the re-entrant corners, even the crack can be, edge crack can be considered as a re-entrant corner. Okay, I will get different intensities of the singular behavior of the solution. In this case, what do we do in order to get an effective finite element solution? Okay, so remember that in this case, if I used the standard mesh that we have, okay, the standard mesh that we have, then uniform mesh, then this will, the solution will be horrible. Actually, the rate of convergence of the solution is said to be suboptimal. Okay, let me erase all this so that I can make the mesh right here. Okay, so what we are talking of is the following, that we have a mesh. Let me make the mesh with some other pen. Okay, let's say I'm making this kind of a mesh. Okay, it doesn't matter whether it's a mesh of quadrilaterals or triangles. Okay, if I use this mesh, so-called uniform mesh, then the solution will converge at a suboptimal rate. That is, we define the quantity. Let me erase this also. We define the quantity strain energy of the U exact minus UFE, square root of that. This is actually equal to square root of the bilinear form of, this is nothing but the error, E comma E. Okay, this is equal to square root of integral over the domain of strain exact minus strain finite element transpose into C into strain exact minus strain Fe dA. Okay, this is what we mean by the so-called energy norm. It is called the energy norm, but you should understand it as the strain energy of the error. That is the difference between the exact solution and the finite element solution. I do not know the exact solution, but if I knew it, this is what it would mean. This will converge in this case as CH to the power of alpha, where alpha was the dominant alpha. I will call it alpha min. So it will be the minimum of the alphas corresponding to each of these singular points. Okay, this is a very strong result, which tells me that in the other case, when there were no corners and singularities, the solution was smooth. That is, if I refine this mesh, okay, so this mesh has mesh size h, that is the elements are of size h. Okay, so if I keep on refining this mesh, add more and more elements, then the error converges as ch to the power of, in the optimal case, h to the power of p, where p is the order of approximation that we have taken. Okay, but in this case, if I have a domain with a crack and a reentrant corner, I will only get ch to the power of alpha min. That is, the rate of convergence is going to be suboptimal. Okay, so this is suboptimal rate of convergence. Okay, so in order to get a good solution, finite element solution, you have to refine the mesh a lot, which means a mesh with which I may not be able to compute at all, because the number of unknowns will be so high that it will be impossible for my computer to handle that many number of unknowns. Okay. Next question that people say is, well, I'm not interested in what is happening here. I'm interested in a region far away from any of these points, either from the crack or from the reentrant corner. Okay, so I know from Saint Venant's principle that the influence of this crack is only in the small vicinity of the crack. Influence of this corner is only in the small vicinity of this corner. Okay, so how does it matter if I'm here whether there is a crack or not? My finite element solution should be good. The problem is that this solution, this badness of the solution here, pollutes the solution here. So if I'm looking at the strain energy of the solution here, and again if I am looking at the error in the strain energy of the solution here, then that will converge as Ch to the power of 2 alpha min. Okay. So what it tells me is that it does not leave me. The nature of the solution, the unsmoothness of the solution elsewhere affects the numerical solution here. Though physically I know this does not happen, but numerically it is going to happen. So my numerical solution is going to suffer. So even if I am interested far away from this crack tip and so on, my solution is bad. At the crack tip, it is certainly bad. Okay, and as an engineer, we are mostly interested in what is happening in the vicinity of these critical points. Okay, so even that argument is not so strong. So we are interested in what is happening in the vicinity of the crack, so that I know whether I want to know whether the crack under a given load, increasing load, dynamic load, becomes critical or not. So that information I would like to know out of the finite element computation. To do that, what is it that we have to do? To do that, we have to do graded refinements. The job is easy, but it has to be done. So-called graded refinements that we had discussed earlier also have to be used. Okay. So what do we have? Let's say we have our domain here. Okay. So what I will do is, in the vicinity of these cracks, I will make rings. These are graded rings in such a way that the radius of the inner ring and the outer ring are related. So I take some characteristic distance, okay, which could be, let's say, the middle line, distance from the middle line to this crack tip, okay. So this could be my characteristic distance, let's say. So this is my characteristic distance, R characteristic. So then this radius, this outer radius will be some q times r characteristic, while the inner one is q squared r characteristic. Similarly, this one is RC, this is for A, this is RC for B. This guy will be q squared, this is RC A, RC B, and this is Q RC B. So I'll make these rings which are geometrically graded, where Q is equal to 0.15 generally, approximately. This is what is taken. This is called the grading factor. Okay. Now I'll make the mesh such that these rings are boundaries which have to be honored. Okay. So now you make the mesh. So one way I can make the mesh is, let's make elements going like this. Okay. And so on. I am not trying to complete the whole job. Okay. So I will make these rings in this way. Okay. So, and then I can complete the mesh. So what do? I do this graded refinement towards the singular corners. Actually, if you see in your solution, even this point will be these 2 points will also be a singular corner. These will be weak singularity points, will be logarithmic kind of singularities. Okay, but these 2 points will definitely also be singular points. So I have to use a graded mesh such that the graded refinements are used in the vicinity of the singular point. Okay, another way I could do the mesh is take the previous mesh here, and in this mesh use some kind of grading here, okay, in the vicinity of the corner, and so on. So there are various ways I could do it. If I do it, then I'll get essentially C h to the power of p rate of convergence. That is, I'll get the optimal rate of convergence. That is, rate of convergence is not such an important issue as far as a user is concerned. What does it mean? It means that for a given mesh, for a given number of unknowns, with this kind of a meshing arrangement, I will get a much better solution as compared to the uniform mesh with the same number of unknowns. Okay, and that is what we are after. That is economy of computations. Okay, so with this approach, with the graded refinements, we can capture the singular behavior of the solution, and then, just like I talked about earlier, in the crack tip, in the vicinity of the crack tip, there are methods by which I can extract what is known as the stress intensity factor, the K, okay, that we can extract with much better accuracy if I use this kind of a graded mesh. Okay, let's look at another issue which is of interest to us as engineers. What happens if I have a domain with curved boundaries? Okay, I'll take a very simple case of a domain with a cutout. Okay, so this cutout profile, let's say it's a circular cutout. This represents a curved boundary. Okay, in this case, if we use the geometric mapping that we had talked about earlier, that is, if we make a mesh like this, if I make a mesh starting like this, let's say I'm making the mesh here, okay, and so on. I'm continuing the mesh in all directions. Okay, then you see that here I'm committing a lot of crime in representing the boundary of the curved surface. Okay, depending on how fine or coarse is the mesh, the error in representing the boundary will be small or big. Okay, in order to, if I use this linear elements, okay, linear geometry, that is the straight edged elements I used, okay, the straight edged element here would lead to a crime in representing the curved boundary. Okay, in order to overcome that error, we'll have to use a very fine mesh in the vicinity of the curved boundary, which is again uneconomical. So can we use a different way of representing the geometry of the elements? That is, can we use curved elements right away in order to capture the geometry better? Okay, so the question is that here, instead of using the straight edged elements, okay, can I use a curved element? Okay, so that this edge is accurately representing the curved boundary here. Okay, in case when I don't have curved boundaries, then all that we have done works perfectly fine. It is only when you have to deal with curved boundaries or curved domains, then you have to talk of curved elements. Okay, so if you see what we had done earlier as far as a representation of the geometry, so geometry mapping was through was linear earlier, okay, while my finite element approximation was a p order approximation. Okay, so remember that the representation of the geometry had nothing to do with my choice of the approximating functions. Okay, we used p order approximation for the finite element solution. We represented the geometry using the linear map because that gave us the exact representation of the geometry. Okay, such an arrangement is, in the language of finite elements, is called a subparametric formulation. Okay, that is, we had a representation of the geometry mapping from the physical to the master. Okay, and remember that mapping was, this is my master element with the psi and the eta, and this is my generic physical element with coordinates x1, y1, x2, y2, x3, y3. Okay, so we had said that x was equal to x1 into 1 minus psi minus eta, which turned out to be the basis functions or the shape functions corresponding to p equal to 1 plus x2 into psi plus x3 into eta, and y was equal to y1 into 1 minus psi minus eta plus y2 psi plus y3 eta. Okay, so this is for any point here going to any point here. Okay, so this was the linear map, while for the approximation of the finite element solution we used, let's say, p equal to 2. Okay, so this was linear, that is, in terms of linear shape functions I could represent the mapping, while for the approximation, this is for the UFE, I could use p equal to 2, 3 and 4. We used it happily without any concern about all these things. Okay, that is what we mean by a subparametric approximation. That is, the shape functions at the element level which are used to represent the geometry are of a lower order as compared to the shape functions which are used to represent the finite element solution. Okay. Now, there could be a situation, especially this is something which is very popularly used, that I have this kind of a curved element, okay, which maps to this master element, which is, again, if you remember, this is the point minus 1 minus 1, this is the point 1 minus 1, this is the point 1 1, and this is the point minus 1 1. Okay, so these are the 4 nodes, we can say. This is node 1, 2, 3, 4. So if I did just using these 4 nodes, then I'll end up getting this representation. Okay, that is, the curved edges will not be properly represented. So what do? We say, okay, fine, let us put another node somewhere in the middle. Okay, we could do a serendipity mapping. Okay, or if I have a triangular element, I will take these middle nodes, that is, I need to know these points in the middle of these curved edges. I need to know their coordinates. So this will become my point 1, this will become my point 2, this is becoming point 3, 4, 5 and 6. Similarly, this will be 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then in this case, I will have the representation of x is equal to sigma xi ni as a function of sin eta. Here I will call it as p bar. Ni corresponding to the order of approximation or order of fit for the geometry given by p bar. If I have taken 6 points, obviously this will mean a quadratic fit. Quadratic representation of geometry. If I have taken 8 points here, it is actually quadratic representation of the geometry here. Okay. So what we are doing is, we are saying that in order to represent the curved edge, we take more points lying on the curved surface and we do a fitting as far as the geometry is concerned of higher polynomials. That is, we are interpolating these curves using a higher order polynomial. Okay, each of these curves on this edge using a higher order polynomial. Okay, p bar in this case is equal to 2. Sigma I is equal to 1 to n corresponding to p bar, number of terms corresponding to p bar, which for the case of triangles will be p bar plus 1 into p bar plus 2 divided by 2, while for the case in the quadrilateral it's going to be dependent on what we had done for the serendipity representation. Okay. Similarly, we'll have the representation of phi. If my finite element solution is also represented using quadratic shape functions, okay, while we are at the same time using quadratic shape functions for representing the geometry, or in the case when the finite element solution is represented using linear shape functions and I am using linear shape functions to represent the geometry, in all these cases the formulation is said to be isoparametric formulation. Okay, so we have something called the isoparametric formulation. Okay, that is the order of approximation for the finite element solution P equals order of polynomial representation of geometry P bar. Okay, let's go back here and see something interesting. My question is the following, that if this was actually a polygonal cutout, okay, then what will happen? In that case, even if you use a higher order representation for the geometry, the representation will degenerate into the linear mapping that we had talked about. Okay, you will see that it will, even though you have used higher order polynomials to represent the edges, you will end up getting all these higher order terms will cancel out, you will end up getting the linear approximation or the linear representation. Second point, if I had used a linear mapping for a curved edge, what problem can it cause numerically? You see that we had discussed a little while ago that these corners are so-called reentrant corners because this angle, if you see this angle, this angle is an obtuse angle. Okay, so you see that all these angles here are obtuse angles. So numerically, that is, my finite element solution sees a domain which has these singular points, which are spurious singular points. It does not really happen in the actual problem. Okay, but my finite element solution does not know that. It sees this domain, the domain that is given by the mesh representation, and it thinks, well, I have so many singular points, and then what happens, the solution, the finite element solution will develop spurious singularities, and you will see that there will be a lot of error everywhere because of these spurious singularities. Okay, that's why it's very important to represent the geometries accurately, okay, for these curved edges. So if I have this curved edge, I'll have to represent the geometry properly in such a way that the geometrical representation, the geometry error is less than the discretization error. In fact, it should be much less. Discretization error. Discretization error means the approximation error. That is what I get when I take the finite element solution as compared to the exact solution of the problem. So this should not dominate my solution. Okay. So generally in the literature, isoparametric formulation is a very popular representation, and for quadratic or biquadratic representations this is often used, and it does a good job as far as representation of the simple curved boundaries that we are talking about. In some cases, when I am interested in using, let's say, large elements, so I want to use large elements here, okay, in that case I may use a superparametric representation. Okay, in that case I can take, let's say I have quadratic approximation, but in order to represent the geometry I use all these points. Okay, so cubic representation of geometry. Of geometry. Okay, that is P bar is greater than the order of approximation P. This is not used normally in the finite element applications because the necessity does not arise, but it may be needed in some application, and if it is so desired it has to be used. The bottom line should be that the error induced due to the inaccuracy of the representation of the curved geometry should not be greater or should not be significant as compared to the error that I am incurring due to the approximation of the exact solution. Okay, so this should be the bottom line with which we have to choose the representation. A place where this naturally comes, this isoparametric representation, is what is normally used. Okay, this comes in when we do the nonlinear elasticity problem, okay, the finite elasticity problem. Okay, using what is known as the updated Lagrangian method. Those things we are not going to discuss here, but in the case of finite elasticity problems, isoparametric formulation is something that becomes almost mandatory. Okay, naturally it has to be used because of the very way we are defining deformations there. Okay. In the next class, what we are going to do is we are going to deal with now a different set of problems. Okay, just like we did in the one-dimensional case, we first dealt with the bar problem, then we went to the beam problem. So next class we are going to do the classical plate problem. Okay, which again, just like the beam, the Euler-Bernoulli beam was, okay, this is an extension of the Euler-Bernoulli beam theory. Okay, it will lead to a fourth order differential equation. Okay, and because of this, it being fourth order, we will have to talk about C1 elements, C1 continuous elements, okay, in the case of such problems. How do you construct these C1 continuous elements? What are the restrictions, okay, of such an approximation? Those things we will discuss in the next class onwards.